Hello and welcome to this calculus video. Today we will be talking about geometric and numerical methods for solving differential equations.
Math 112.
As I mentioned in the last video, many differential equations are hard or even impossible to solve. We can still learn a great deal about a differential equation from certain geometrical or numerical approximations. All of our techniques for this video apply to first-order differential equations in the form y prime equals f of xy. For instance, y prime equals x plus y. So we will assume our differential equations come in this form. Firstly, we will talk about slope fields, also called direction fields, which are a way of approximately sketching solutions without finding an exact equation. The idea is that if we know the solution goes through the point xy, then we also know the slope there, because y prime equals f of xy. So we could draw a little line at the point xy with the slope f of xy, and a solution going through that point would have to look close to that straight line, at least nearby. Let's look at this more closely for y prime equals x plus y. At the point 1, 1, we know y prime equals 2. So at the point 1, 1, we could draw a little line segment with slope 2. If we apply the same process to many points, then we can get a general feel for the way the solution curves evolve, and we can approximately sketch solution curves by following the directions of the lines. The geometric process of drawing a direction field lines up closely with a numerical method called Euler's method. To use Euler's method, we start at some initial condition and proceed in the direction indicated by the slope field for a small step. We then look at our new location and proceed in the direction indicated at this new point for another small step. This method is not exact, but if our step size is small, then we can approximate the solution curve reasonably well. To formalize this process, we start with an initial condition x0, y0, and have some small step size that we will call h. We then iteratively define x sub n to be x sub n minus 1 plus h, and y sub n to be y sub n minus 1 plus h times f of x sub n minus 1 y sub n minus 1. In our example y prime equals x plus y with initial condition 1, 1 and step size 0.5, we would initially set x sub 0 equal to 1 and y sub 0 equal to 1. We then add the step size to get x sub 1 equals x sub 0 plus h, which is 1.5, and then use the differential equation to find y sub 1 equals y sub 0 plus h times f of x sub 0, y sub 0, which is 1 plus a half of 1 plus 1, which is 2. We could then take another step and find x sub 2 equals 2, and y sub 2 is 2 plus a half of 1.5 plus 2, which is 3.75, and so on. In practical applications, we would write a computer program to do this for us. There is a certain class of differential equations for which we can draw a different kind of picture. We call a differential equation autonomous if the independent variable does not appear explicitly. So for instance, an equation that involves just y's and y primes, but no x's would be autonomous. But our example y prime equals y plus x is not. Autonomous differential equations occur in many physical applications, and they often express the idea that the law being described doesn't change as time changes. If we have an autonomous first-order differential equation in the form y prime equals f of y, then it doesn't make sense to draw a direction field with 2 dimensions, because all of the lines for a given y value will be parallel, as there is no dependency on x. In these cases, we often instead draw a phase diagram, or phase line. Here we just need a y-axis, which we can either draw horizontally or vertically. At a given y, there are 3 possibilities for the value of y prime equals f of y. It is either positive, negative, or 0. If it is positive, then y is increasing, so we would expect a solution curve to increase. If it is negative, then y is decreasing, so we would expect a solution curve to decrease. If y prime equals f of y is 0, then we have found a special kind of solution called an equilibrium solution. An equilibrium solution to a differential equation is a solution that is constant. To draw the phase diagram, we mark all the equilibrium solutions by solving the equation f of y equals 0, and between them we know that y prime does not change sign. It is either positive or negative, so we draw arrows pointing in either the positive or negative direction accordingly. For example, the differential equation y prime equals y times y minus 2 has 2 equilibria, y equals 2 and y equals 0. By plugging in, we find that y prime of negative 1 is positive, y prime of 1 is negative, and y prime of 3 is positive, so we mark our in-between regions with corresponding arrows. We would expect solution curves to evolve over time by following these arrows. The direction of the arrows allows us to classify the equilibrium solutions as stable if the arrows at either side point in, unstable if they point out, or semi-stable if they point in the same direction. Equilibriums that are stable tend to attract solution curves to them, whereas equilibria that are unstable tend to repel them. For a simple example, consider a swinging pendulum. It has two equilibria, one where it is hanging at rest vertically down, and one where it is hanging at rest vertically up. The first equilibria is stable because if you nudge the pendulum slightly from rest, it will stay close by. The second is unstable because if you nudge the pendulum from rest, it will move away from the equilibrium. That's all for now, folks. Today we talked about drawing slope fields for a first-order differential equation and approximating their solutions numerically using Euler's method. We discussed autonomous differential equations, a special kind of solution called an equilibrium solution, and how to classify these using a phase line.
Math 112.